What if gravity is not a force? Modern physics discovered something extraordinary. In Newtonian physics, gravity behaves like a force, but in general relativity, gravity is described by the curvature of spacetime produced by mass and energy. Einstein arrived at this idea through the equivalence principle. In a sufficiently small region of spacetime, the effects of gravity and the effects of acceleration appear identical. If gravity were a force, we should be able to distinguish its effects from those of acceleration. But according to the equivalence principle, standing on the surface of a planet is locally indistinguishable from accelerating in a rocket in the complete absence of gravity. In both cases, the observer feels pushed toward the floor, even though the first situation is caused by gravity, and the second by accelerated motion. This suggested that gravity might not be a force at all, but a consequence of motion within curved spacetime. But what changes the geometry of spacetime and curves it? Space and time are not separate things. They form a single four-dimensional structure called spacetime. But spacetime is not rigid. Mass and energy change its geometry. So falling objects are not being pulled by a force. They simply follow the natural paths allowed by this curved spacetime geometry. Physicists call these natural paths geodesics. Even light follows these paths. When light passes near a massive object, its trajectory bends. Spacetime tells matter how to move. Matter tells spacetime how to curve. But curved spacetime does not only affect the paths objects take through space, it also affects how time flows. In stronger gravitational fields, the closer a clock is to a massive object, the more slowly it runs compared to one, let's say, farther away. This was observed when scientists measured the tiny redshift in the frequency of gamma rays caused by Earth's gravity. This effect is called gravitational time dilation. But what happens when we move from tiny shifts to the extreme? If enough mass collapses into a small region, spacetime becomes so strongly curved that nothing can escape it, not even light. These objects are called black holes. They form when massive stars collapse under their own gravity at the end of their lives, compressing their mass into an extraordinarily small region. And what happens if a violent event, like a collision between black holes, shakes spacetime itself? Ripples in the spacetime continuum form. They are called gravitational waves. They were first directly detected in 2015. During this event, roughly 3 times the mass of the Sun was converted directly into gravitational wave energy. For a brief moment, the system exceeded the luminosity of all the stars in the observable universe combined. We saw how general relativity reveals a remarkable picture of the universe. What we feel as gravity is simply the geometry of reality itself. If spacetime itself can bend, ripple, and ring, what else might the fabric of reality be capable of?